Okay, so what we are going to do today is we want to understand the mechanism of the Fokker-Planck equation, and especially the relaxation of velocity and the fluctuation of velocity of a Brownian particle, which I'll soon remind you. But we want to explain it from a more microscopical point of view, which means that we want to introduce some mechanism that will show us how the friction comes into play and how will the fluctuations come into play. And this general method is a derivation of the well-known results, both of Stokes, if you want, and of the Fokker-Planck equation, and actually also of the equilibrium of Maxwell distributions. We'll get all this from a collision process. So these type of collision models were considered by Boltzmann when he started statistical physics, when he looked into the problem of entropy increase. And Boltzmann created something called the nonlinear Boltzmann equation, which is a very complicated equation describing how gases evolve in time, how the probability density function of finding the gas with some velocity, how does it evolve with time. This is a nonlinear equation which you cannot really solve. It's very difficult. So what we are going to do today, if you want, is a simplification of Boltzmann ideas to a simple model, which is still complicated enough and interesting enough for our goals. So let me define what is our goal, and then we'll define what is the macroscopical model. So let us first think as physicists. So we have a Brownian particle of mass m and in a bath of temperature T. This particle is moving in space, but we are interested in the velocity of the particle as a function of time. And we already said from macroscopical considerations that we know many things. We know, for example, that the average velocity decays with time t, and that this decay rate, this is an exponential decay rate, is given by Stokes' law. So we have a dynamical equation for the average, which is very simple. The solution of this is an exponential decay with this rate gamma. So one thing we are interested, we want to know what is this gamma. Before we just said here is this gamma, but now we want to see how, if we can get it from some microscopical picture. And what do I mean by microscopical picture? So microscopical picture, let us think what is really happening here. So we have a very big particle, and then around it we have very small particles. What are the small particles? These are the small particles of the water. But you can think about this as some particle. Let's say there is a gas. It's easier to think about a gas around here. That's what actually I will do. I will not really consider water. So we imagine that here we have other small particles, and they have many of them, and they are going to collide with this particle. These collisions, they sometimes come from the left, they sometimes come from the right, etc., etc. So we have collisions, and they lead to two things. They lead, first of all, to the dissipation, because let's say you have a velocity of the particle and it's going in this way, then it collides more with particles from this side, and then it will slow down, and on average you'll get an average velocity which is 0. So this is what I mean by dissipation. It will cause you the dissipation, but in addition there is fluctuation. So this is the velocity which is random as a function of time, because sometimes you have more collisions from the left, sometimes you have more collisions from the right, and this is a stochastic process because you have many gas particles, and you know life is a little bit random, so sometimes you get hit more from one side than the other, and then you have these fluctuations. So the collision leads both to the fluctuation and to the dissipation. So you cannot separate. The collisions are giving you both these things. And this is not so surprising anymore, because if you understood the idea of philosophy of Einstein relation, he also said that the fluctuations and the dissipation are related one to another. Why they are related? Because what is happening here is that you have these small particles impinging on the big particle, and that has to slow it down. So if we look at this velocity very carefully, if you think about it, there is a typical time, we're going to assume there is a typical time between collisions. So the particle is moving freely, then boom, it collided, a gas particle is colliding with it, it moves freely, etc., etc., etc. Between collisions, the velocity of the particle is a constant. So if I would be very, in principle at least, strict, it would be, the velocity process would be something like this. What I mean by these straight lines is, here I got a collision. The collisions themselves, we're going to assume, are very fast. What do I mean by collisions which are very fast? It means the following, that these small particles here, I'm going to assume that, let's say, they are something like hard spheres. Hard spheres come, they collide, and then they depart, and this collision, the time of the collision itself, I'm going to say 0, and that's why between collisions you have such a motion. Of course, if you had, for example, in water, if you had some long-range interactions where all these particles are always interacting with this guy, then this idea even of collision is not clear, because in water, let's say at a given moment of time, it's not true that only one particle is colliding with a big particle. It's all the particles are interacting all the time with the water molecule. That's why looking at this as a gas, like Boltzmann did, at the beginning is very, very useful. To be honest, we cannot really solve water because it's so complicated, because water is always interacting with this guy. Maybe with a very powerful computer you can solve it for some short times, but in general we want to assume that these collisions are in some sense rare. See, free motion, tuck collision, something like this. Now this is the idea. Of course we will have some knob describing how strong the collisions are. This we will need to define. So the typical time between collisions will be something like an average time between collision. And we will assume that this average time, that I know this average time. So this is a simplification. This average time itself is complicated because it depends, for example, on the size of the particles. It depends on the temperature itself, because if the temperature is high, then these particles will move intuitively faster, then they will collide more often. So this by itself is going to be a complicated function, which we are not going to deal, because we want to deal with some of the problems and not with all of them. And this I'll later denote by R, 1 over R. So R is the rate of collision. How strong are the collisions? This will be determined by some epsilon. Soon we'll define this epsilon. So let us now define the model. So the first assumption is we want to make it as simple as possible, but not too simple. We will work in dimension 1. This is going to help us tremendously and make this a solvable model. We're going to assume we have some gas particles And they have a velocity distribution which I'll denote by FVM. The small mass m is the mass of the gas particles. So we have a velocity distribution. I'm not going to specify it at the beginning, but later I will. And what is the easiest assumption that you can make? What is the velocity distribution of the gas particles? Well, you have a temperature T. So the easiest assumption is to say, okay, these gas particles, if you want to think about it, they are themselves Maxwellian. And this scale, this FVM, describes the distribution of these gas particles. And what is the scale? This is simply the temperature. This is how I define the temperature. What it means is that these particles, for example, go and they hit these walls. These walls are the walls of all the system, like the walls of the room here. And these walls are at temperature T. They collide here in a very complicated way. And then they come out with the velocity distribution, which is, this is an example, these are Maxwellians. But they are Maxwell. What is if they are Maxwellian, what is the Vm squared? First of all, V average m is, of course, equals 0. We will always assume that the velocity distribution is symmetric and has mean 0. What will happen if we break this guy? What will happen to the big particle? It will drift. It will just go in one direction. So in principle, you can do that if you have some particles that are going from there to here. You can move this big particle by collisions in one way. But we are not considering this. So we are going to assume that the average velocity of the gas particles is 0. In fact, we are going to always assume that this function is symmetric. So there is no special direction in space. Otherwise, you might have something very distorted here. It's not natural. There's no reason to assume that left is better than right and right is better than left. But what is this guy? If it is Maxwellian, this is simply given by the equipartition divided by small m. So this will be the velocity squared according to the equipartition. Equipartition, to remind you, is according to ordinary equilibrium statistical physics. The velocity distribution is given by the kinetic energy is given by the kinetic energy divided by temperature in the exponential, which is the Boltzmann-Gibbs measure. And that means that the average velocity of the particle is given by k Boltzmann T over m. And again, this is the equipartition for the kinetic energy, actually. So we know something on the velocity magnitude of the gas particles. Now, we will do things in two ways. Now, okay, but first let us assume that you have the Maxwell distribution for the gas particles. This will be model, call it model 1. Then the question is, what do we expect? We have here Vm. So capital Vm, this will be the velocity of the tracer particle. The tracer particle is the big particle we are following. This is the Brownian particle, and it has a mass capital M. So M, capital M, is the mass of this particle. So in this model, we already have two masses, small m and big M. And both of them are important. So the question is, what will happen? What is, in the long time limit, the PDF of Vm? let's say when t goes to infinity after we define all the collisions. First of all, what do we expect? In physics, we always know something to expect. We always cheat a little bit. What do we expect? If this guy is Maxwell distribution, we hope, otherwise something's wrong with the physics, that we can define a model where the velocity distribution of this capital VM is also Maxwell distribution. It's not trivial. I want to say that Maxwell distribution, in my opinion, is not trivial. Why is it not trivial? Because it's independent, for example, of the small mass. So the Maxwell distribution, or what we expect, is to find that the PDF of VM is equal in the long time limit to the usual Maxwellian, which is Vm squared m 2k Boltzmann t. And here we have the normalization, the usual 2 pi thing. And the question is, but why should this be M independent and R independent? It's not at all obvious, in my opinion. I mean, we know that this is the result, but this is a beautiful, really unbelievable result, that the Maxwell velocity distribution does not depend, it doesn't care at all what is the environment. You can put here temperature, you can put particles in any mass, it doesn't care. So we are going to show that this is the case, or we are going to use some assumptions that will kind of justify this, and you will see that this Maxwell velocity distribution is a combination of A, physics of the collision model, and B, it will be something like the central limit theorem. And it's not a surprise that this Maxwell is actually a Gaussian. You'll see that we add random variables. What are the random variables we are going to add? So what is happening here? You have a particle, mass big M. It collides with a small particle. It changes its velocity a little bit. We'll soon and then it collides again. It changes its velocity again a little bit. And another collision, and another collision, and another collision. So when do we expect equilibrium? We expect an equilibrium when we have many, many, many collisions. So when I say long time in equilibrium, what do I mean? I mean t to infinity is a time which is much longer than t times this rate r has to go to infinity. And if you have many, many collisions, what we are actually going to add is, in some sense, the velocities of the gas particles, which will influence the velocity of the massive particle. And you will have many of them, many collisions. So let us define this now. But before doing that, we're going to later on, we're going to do a second model. We're going to say, let's say, this is a theoretical thing. Let's say FVM is not Maxwellian. So, you know, maybe you guys, maybe you are correct. You say, okay, here, if I put a Maxwell distribution for the gas particles, then I will get this guy. Okay, maybe this is not a big surprise. We want to show it. It's nice, R independent, mass independent, but we know this result. But if FVM is not Maxwellian, will the big particle relax to Maxwell distribution? That is a much deeper question in some sense. So you see, it's very similar to the central limit theorem. What did we do in the central limit theorem? We said the Gaussian one. You sum IID random variables. You don't care if these IID random variables, they come from a Gaussian, they come from a uniform distribution, they come from an exponential distribution, they can come from any distribution. You sum many of them, and oops, you get the Gaussian when you rescale correctly, right? And what we want to show here, under a certain condition, that no matter what is the velocity distribution of the gas particles, do we still get, and the answer will be yes, Maxwell for the particle M that we follow. This is a notion of stability. What does it mean? You don't care with what you start with, what is the velocity distribution of the gas particles. After many, many collisions, if you reach equilibrium after many, many collisions, which means that the collisions have to be weak in some sense that are going to define, you will always get this Maxwell distribution. Now, why is this important? Because let's say these small particles actually are also interacting among themselves. They are interacting with something else. It's very complicated. But it doesn't matter, because once they interact with something else, even if it's not Maxwellian, but it has a typical velocity, eventually the Maxwell distribution is like an attractor. Like the Gaussian was an attractor for the summations, like the Levy was an attractor for summation of IID random variables. So will be the Maxwell distribution. It's very similar in some sense, and this is what we want to show. You immediately can ask the question, is Maxwell unique? So I'm going to tell you, if you have some assumptions on the velocity distributions, if they are power law tailed, then you don't get Maxwell, then you will get, what will you get? Levy, of course, Levy. It's either Levy or Maxwell, it's either Gauss or Levy, but of course, this is a strong assumption that the velocity small mass distribution has a Levy. But if they start somehow with a power law, then of course, the second moment does not exist. It's infinite. Then you will get a Levy distribution as an equilibrium. But that's a different story. But once you understand that all of statistical mechanics is a central limit theorem in some sense, and if you are really interested, there is a fantastic book by a guy called Khinchin, a famous guy, Russian mathematician, from Wiener Khinchin, good. So, and he wrote a book, he's a mathematician, but he wrote a book explaining how all statistical mechanics come from the Gaussian central limit theorem, if you're interested in this. And you see it in many ways. I mean, it's not so difficult to understand this. But it's a very special central limit theorem. Okay, so now we have to add more assumptions. You see, this is a real world problem. It's very difficult, I mean. So we are going to add more assumptions. Maybe I mentioned, first of all, R is independent of velocities. So this is a kind of mean field. So I'm not going to assume that when the particle, let's say the massive particle, is fast, it collides more with the other particles. You can imagine if you have a very high velocity, you are moving very fast in the gas, you collide more. So the rate of collision depends on your velocity. Here we're going to assume that this rate is independent of velocity. This is actually valid when you move very slowly. And this is also what I'm going to assume soon. I'm going to assume also that the mass m is much bigger than the small mass. Now, we will solve the problem in generality when the masses are the same. We can also solve this. But this is the most important limit that we are interested in. This is the massive particle, this big one. These are the small gas particles, and we assume that the big particle has a mass much bigger than the small particles. This is very natural. For example, we follow a very big Brownian particle. It can be only 1 micron, but it's still much bigger than the gas particles, which are angstrom size. So this is the assumption, and this is what we are interested in, and this also means that this guy is slower compared to these guys. We also assume that each gas particle collides only once with the tracer particle. What does it mean? If you look at this picture, imagine this particle A collides with this guy, but then somehow they meet again. If they meet again, this particle, we call it sometimes the Bass particle, remembers the previous collision with the massive particle. You change its velocity, and now he remembers that in the past, this guy, through the collision, he remembers the old velocity. In that case, you will have a memory effect. So each time you need to ask yourself, did this particle collide in the past? And this gives you these memories, which are A, very complicated. But secondly, if this mass is small, what happens? It comes and collides, and then it scatters off. And then it goes to infinity, if this is a gas. And then it collides back with the bass, which is on the boundary. And then it changes its velocity again. So when it will come back, boom, it will not remember. So this assumption that each gas particle collides only once with the tracer particle is good. It means that each time they collide, you draw, this means that we draw the velocity of the gas particle from what I defined previously, but now I'm explaining what is the meaning of this condition, from FVM, which means if you had some memory and this gas particle is, let's say, moving very fast and it's heating all the environment. So if you have a dense enough environment, you have a massive particle and it moves very quickly. It transfers energy and velocity and momentum to the gas, and then the gas is heated. If this gas is heated, you are going to change this F of Vm. So what we are going to assume that this gas is very dilute in some sense, and then each time you collide, you go far away, and then you don't recollide, and you don't have this memory effects. We also assume in some sense that the Bass particles are non-interacting. So I'm neglecting collisions between the gas particles. If they are very small, they don't see each other, they see the big particle. If you just throw away one of these assumptions, you make the problem unbearable, for beginners at least. Okay, so let us define the model. Okay, but before that, one of the most important assumptions are collisions are elastic. This plus 1D helps us solve the problem. Elastic collisions, I mean, very simply, they conserve energy and momentum each collision. In that case, we're going to define V of the mass particle plus. This is, again, the big mass is the tracer particle. This is the velocity of the tracer particle after collision event, immediately after. So the meaning of the plus is I had a collision. This is immediately after that. Of course, later on the velocity will be conserved, but this is this plus. Vm minus is simply the velocity of the tracer particle just before collision event. So because the collisions are elastic, then we know from high school that the velocity of the particle just after collision is some psi1 Vm minus plus psi2, and here I have, maybe we add a tilde now, Vm is the velocity of the gas particle. So this is the velocity of gas particle. This describes one of the collisions. So let's say this is the collision number 222. Then in this collision 222, we add the velocity of the gas particle. What is this velocity? This velocity is random, but for this specific collision, it is a number. What is the distribution of Vm? This is given by the PDF of Vm, as I mentioned already, is given by this function FVM. And if you want to think about this as a Maxwellian, then fine. Okay? What is this psi1 and this psi2? This you solve the equation. You did it in high school. This is you solve the conservation of energy, and you solve the conservation of momentum when two particles collide quickly. So you have two equations, conservation of energy and conservation of momentum, and you have the velocities of the particle before collision, two of them. So this Vm actually is the velocity of the gas particle just before the collision, because we don't care what happens after the collision, because after the collision it goes to the bath, it goes away, we don't recollide. So this is the velocity before the collision. And then you have the velocity of the gas particle before and after the collision, the velocity of the massive particle before and after the collision. But you have two equations of motion, and then you can get rid of the sum of their variables, and then you have here Vm plus as a function of the velocity just before. And from this conservation of energy and momentum, you get psi1 and psi2. This psi1, if I remember correctly, this is 1 minus epsilon, 1 plus epsilon, and psi2 is 2 epsilon over 1 plus epsilon. If you don't remember this, well, you did it. I think everyone knows this. Yeah. And what is epsilon? Epsilon is the ratio of the masses. So when the gas particle has small mass compared to the tracer particle, epsilon is a small number. It's a small number, and you see what happens here. Let's look at the first term, psi1. Psi1, if epsilon is small, is a number which is roughly 1. So if you have a very massive particle, as you all know, I hope, after the collision, you get nearly the same velocity, because this is 1. So when the collisions are weak, you are not changing a lot the velocity, because a small particle cannot change much the velocity of a big particle. It's as simple as that. Already here you see more or less why you get this exponential decay in this model. What is the average of Vm plus? So Vm plus average. Average over what here? What do we average over? We average over these velocities. This is the meaning of the average right now. So the average velocity of the gas particle is 0, right? So this is equal to psi1 Vm minus. So if I want the velocity average after n collisions, this is given by psi1 to the power n, the initial velocity. So v0 is the initial velocity. Right? Because Vm after the first collision is psi times the initial velocity. Then the second, after the second collision, you need to multiply it again by psi1, psi2, psi3, etc., etc. If the number of collisions is 0, then the initial this is going to be simply the initial velocity. And what is this law? This is an exponential decay, similar to what you have here. But here we have n. What is n? It's a number where you measure collision number 1, 2, 3. So this is the number of collisions. Assuming, let's say, we have 22 collisions, this is the average velocity. So, of course, in real life, what is n roughly? N is roughly the measurement time divided by the time between collisions. That's the estimate of this n. And then you'll have an exponential decay for the mean. And you all see this simple exponential decay for the average. Of course, the average, when n goes to infinity, this number is less than 1, any epsilon. And then, boom, it goes to 0. And you know that, of course, because you are colliding from left and right. So you expect that the average velocity after many collisions, when n is very large, is going to be 0, because then you cannot go in one direction. At the beginning, you can go in some direction, let's say plus. But after so many collisions, this will just vanish, and you'll have this exponential decay due to the collisions here. All this is valid if you wanted temperatures 0, when all these velocities are 0. But we are not. We are more interested in what happens, the combined effect of these two things. So what is this? What is this object that we have here on the blackboard? It's a kind of transformation. This is a definition of the model, if you want. So let us define it now more precisely. Now define it in time. So what do? You step 1, generate initial velocity. You need to tell me what is this initial velocity of the tracer particle, capital V0. Step 2, find the time tau 1 for first collision. Let's call it tau 1. What is the PDF of tau 1, or the PDF of tau in general? We're going to assume this is this rate assumption, that this is given by exponential distribution. So the distribution of times between collisions is going to follow an exponential law. This is tau. This is this PDF of tau. This corresponds to the assumption that each collision is totally independent from each other. So this is like radioactive decay, if you want. There is no memory. This is an assumption. You can do all what I'm going to talk about if you modify this assumption, but this is the most natural assumption that people used, let's say, at the beginning of the theory of gases. It's called Drude model, if you want. Maybe you heard about Drude in the context of condensed matter. It was used by Maxwell and Boltzmann and all these guys, because it just says what is the probability of your arrival at a small epsilon is given by this rate. and then you generate it. It's very easy to generate, let's say, on a computer, this tau 1. So if R is of order 1, then the average is, of course, 1. You use this and you generate this. Then you have the first collision. So V of t is equal V0 for times t less than tau 1, and for times between tau 1 and tau 1 plus tau 2, V of t is equal psi 1 V0 plus psi 2 V tilde m of the first collision. And what is Vm? So now we need to generate Vm1 from Fvm. So you are given, this is part of the model, you know this distribution. Again, maybe this is Maxwellian. You generate this random number, and now you know the velocity of the particle. So if microscopically it looks something like this, V of t, it's V0, and then it goes to V, maybe we call it V1. This is after the first collision. This time is tau 1. And then I have the similarly tau 2. And this, in principle, it can go up if you want, and then something like this. This is a function of time. So we have on the time axis, we have tau 1, we have tau 2, we have tau 3, and here we have the measurement time. We stop it. And this is collision number 1, this is collision number 2, collision number 3. So the number of collisions is random. But actually you know, or you should know, what is the distribution of the number of collisions. If you have this distribution as the time between collisions, the distribution of the number of collisions is given by a very famous law. You know it, or do you don't? Poisson distribution. So we know how many collisions are in statistical sense. And in some sequence, measurement time t, let's say, is long. The number of collisions can fluctuate. This n, let's call it n, number of collisions is random, but it will come from Poisson statistics based on the assumption here. And then, of course, 5, we go back to step 2, which means that, of course, we don't generate tau 1 now, we generate tau 2. You generate again a velocity, now it will be Vm2, and you continue like this until you generate a tau that the total measurement time is bigger than t. And then you stop the process because you observe the system at time t. This is continued until some up till n plus 1, this is not a mistake, is bigger than t. So you generate one step that comes over here, and then you say, oh, it's already past my bedtime, here is my measurement time. Then I stop it and I eject this loop, and this is how I can create, in principle, this type of stochastic process. Now, this stochastic process is called the jump process. It has discontinuities in the velocity. You see, it jumps from here to here, it jumps from here to here, and this comes from this iteration rule. And this will be true because when these masses are not, this epsilon is not small. But what will happen when epsilon is small? You see these jumps will be smaller and smaller. These heights, these discontinuous jumps, when epsilon is small, this guy and this guy, when epsilon is small, these guys will be compressed. So to get a relaxation at all, what happens, let's say, when epsilon is 0? Well, nothing happens, obviously, because the mass of the gas particle is 0, so it doesn't collide. The big particle doesn't see it at all. So to define a sensible limit which describes relaxation when this epsilon goes to be small, this is the limit that we are interested in. So when epsilon is small, this we call collisions are weak collisions. And then we need to take R to what? R to infinity to get some impact on the massive particle. So to describe the system with something like a Fokker-Planck equation, we need collisions to be frequent, very fast. That is, the times between these two guys is very short, but weak. Here we get the Fokker-Planck equation. This is a very natural thing. Again, if you have, let's say, a massive particle, a Brownian particle is big compared to the surrounding particles. So these assumptions are, this epsilon to 0 limit is reasonable. It happens in many cases, but it's not a rule of nature. In principle, you can look at a system which is all the masses are the same. And then what will happen? Well, you will not have a Fokker-Planck equation. You will have a Boltzmann equation. You will have a more complicated equation describing the dynamics, because you have jumps. You have discontinuities in the velocity in this model. Because, and again, why do you have discontinuities? Because I assume that the collisions are super fast. So these jump processes are, generally speaking, are not described by Fokker-Planck. So in Fokker-Planck, you have the second derivative of velocity, the first derivative of velocity. It's something that you are used to. You have eigenfunction expansion, as I showed you already. And this is because you have very small changes. When you have a jump process, you have something else. And this something else, the mathematical description, is integral differential equation. And this is sometimes called a master equation. Only the masters can treat it. The ordinary people can go to Fokker-Planck. The master equation is, beyond the master equation, there's one equation called the Boltzmann equation, which is also nonlinear. So all this is in kinetic theory of gases. The master equation is, many times you can write it, not always you can solve it, but we always think in this way. The real truth, and this is a truth after so many simplifications, is described by this master equation that I'll soon write down after I define the model. And from the master equation, we can, in some cases, simplify the master equation and then have the Fokker-Planck equation. So Fokker-Planck equation is the lowest level type of description of the kinetics. But it's the most practical because, and it's a very good approximation in many times, but it's not the fundamental thing, if you want. But it's the practical thing because that's the thing that we can many times treat, but we always need to understand that the Fokker-Planck equation is an approximation by itself. Because you know what, guys, life is complicated. You understand that gases and real systems are complicated. Okay, so now maybe we'll go for a break, but before that, did you understand the model? The model is clear? Yes? No? Clear? You understand the model? Okay, so now we need to write, this is what we're going to do later, this, after the break, we're going to write the, this is the equation for W capital VMT. What is this equation? Well, you know what's this equation. This is going to be a master equation, but in the break you can tell me how does this equation look like. What is the equation? I define the model. What is the equation for the probability density function of finding the particle with velocity capital VM at time t? If anyone has a suggestion, he gets 10, well, maybe not, it's in my web. So we want to use all the assumptions that were outlined in the previous lesson and write down an equation of motion for the probability density function of the velocity. We want to know how it evolves in time. And for that, we use the fact that we have this rate approach. So what the equation reads, this is the master equation. So this is the PDF, the normalized function of VM. This is the big VM t. It's changing in time. Let me write down the equation. The first term is going to be,
what's W?
W is the PDF. Usually it was P, but W is the PDF of the velocity of the particle. So WVMT is the PDF of VM. It's a normalized function, and at time t equals 0, W is equal to a delta function over V0. As I mentioned already, we expect that this distribution will go to if the velocities of the Brownian part of the gas particles are Maxwellian, we expect this to go to a Maxwell distribution. So I'm just going to write down the equation, and then then I'll discuss its meaning. So rate, remember rate, one of the rate is the time between collisions that enter in. So this describes how often is the collisions. So a high rate, R large, means time between collisions small. And here I have the following equation. dVm minus integral dV small m integral. So we have two integrals, W Vm minus t, the velocity of the gas particle, the distribution of it, times delta function, which gives you Vm minus psi Vm minus psi1 minus psi2 Vm. Essentially, this is the most important equation in this lesson, at least as a starting point. And you see, as I mentioned, it is an integral differential equation, and it has two terms. So this is how this function is changing in time. And the first term is relatively easy to understand. If there are two processes here. Let's say at time t equal some time t, your velocity is some Vm. So you have a rate, and then you get a collision. And if you get a collision, it will change. It will be something else because it hit. So this says, OK, I'm going to go through a collision event, and then Vm will go to something else. You don't care to what it goes. It just collides. It goes to some other velocity. Why don't you care? Because this is this minus sign. The minus sign is I have a process where my velocity is Vm and now it's something else. So imagine you are in the room and I'm looking at the number of people in the room. There are two ways. Either some guys will leave or some guys will enter. The same with the velocity. The velocity is Vm. Sometimes you leave this velocity. How often and at what rate? This is given by this minus r. And you don't care to where. I don't care if you leave this room, if you go to, I don't know where, I don't care. Wherever you go, you just leave, and this means that you reduce the population of particles with Vm. So you go from Vm to something else. This is the opposite. This is you had some velocity Vm minus. What is the probability to have a velocity Vm minus? That is just before the collision. It's given by this thing, which we are looking for. Now, to go from Vm minus to Vm, so this describes going from some Vm minus, and it can be many different Vm minuses, given by this distribution, which depends on time. How do you go from here to here? You need to collide with a particle. And here is the rule. If I have Vm minus and I have this Vm, then this is just the conservation of energy and momentum. I'll go to Vm. I hope everyone sees this is just the collision here. So, but these has weights. The weights are what is the probability to have this Vm tilde. This depends on this function here. What is the probability to get this Vm minus? It depends on W itself. So that's why I need to sum or integrate over all the possibilities of the Vm minus before the collision and all the particles, the velocities of the particles that are colliding. Each one has a different weight and this collision rule. Is this clear? Again? From when? From the beginning of class? This was clear, the first one? Ah, that's your fault. So again, this is a lost term. This just describes, it's a bit difficult for me to repeat because I don't understand what's not clear. But you have to think about it. Let's say you have a particle with Vm, and then you collide with Vm tilde. This is one process. And this is exactly this Vm. Then this guy goes to Vm, this was Vm minus, this goes to Vm plus, something else. This is one process where you lose a population. So the way to think about it is, think about this as a histogram. You have ensembles of particles, many tracer particles. So I build a histogram of this, which means I have many particles with some velocity Vm. So I think about it, this W as some shape at some time t. But I make it bins. So this is Vm, this is W. And of course there is a small surrounding, but if I'm here, I can go to here, I can go to there, I can go to here, etc. I can go many places. How do I go from this Vm? I simply collide. And then what is the rate of collision? Here, this is the rate. So this is the rate that you lose population from a particular velocity and you go somewhere else. It can also be from here or here. So for different values of populations, of course, this W is changing. So if you have big amount of particles in one bin here, you can lose more, of course. That's clear? I hope. This describes exactly the opposite. You want to go into this Vm. So you have something Vm minus, and then you have something, and this goes into Vm. What is this Vm? This Vm is this Vm. So you have processes, let's say, that take you from here to the velocity you are looking. And of course, there's nothing special about this velocity. It goes from anywhere to anywhere. That's why you have these integrals, which are summations. So how is it done? You need some velocity before the collision, and you need some velocity of the colliding particle. Given these two values of velocities, they will land you in the right position Vm, and this is just the transformation rule or the elastic collision rule. So it takes you for, give me one value here, give me one value here, and then you will get into here. But these two values, Vm tilde and Vm before the collision, are distributed. But what are the distributions? They are given by the velocity of the gas particle and the velocity of the massive particle before the collision. Then you need to integrate over, because you can come from many different directions into the point you are interested in. And it's done also with the rate. This is an assumption. If the rate would have depended on velocity, you can do that. Then you will have here a rate-dependent velocity inside here. Then the equation will be even nicer. But that's a different story. So you can imagine that this rate will depend on the velocities or the relative velocities. Then it will be inside here. If you're really interested, I can give you many references on that also. Yeah.
Why is the process of getting into VM is like with collision, but the process of getting out of VM is not?
Because if I give you a flick, you're getting out. It doesn't matter how big the flick is. You're just moving out, right? That's it. So if you want, you can have here FVM and integrate over the VM, but that will give you 1. But going out is independent. You are at this point here. Any collision will kick you out. That's why the first term is easier. Okay, so this is the equation. And of course, this is, as I already said, this is the master equation, integral differential equation. It's doesn't look like a Fokker-Planck equation. I hope all of you agree. So one of the questions is, how do you get a Fokker-Planck equation out of this? So we're going to slowly solve this equation. So the first thing to do is, okay, I have here two integrals over the velocity of the gas particle, of the velocity before the collision, but I have a delta function. So, okay, if I have a delta function, one of the integrations is going to be trivial. So we will do this. I hope you understand how to do this. But, I mean, the way I like to do this is, I mean, one way of seeing this is I have this delta function, psi1, because, okay, this is the small problem. This is not a big problem. You see, let's say I want to integrate over Vm minus. I have here this psi1. So you need to understand that when you have a delta function, you want to transform. You want to have Vm minus, for example, and then you want to integrate. And then you want to get rid of this psi1. That will give you something in the Jacobian of the transformation. So just let us see this briefly. This is Vm minus psi2 Vm tilde. This is, for example, this is a representation of the delta function. But I think you all know this. Eik. I just write down what is this. Delta function, Vm minus psi2 V gas particle, dk. Then I write this as 1 over 2 pi integral from minus infinity to infinity, e to the minus I k psi1 V m minus. I just take this psi1 out. But now I have Vm psi1 with a minus. And here I have plus psi2 over psi1 Vm tilde dk. Now I define k times psi1 as k tilde, maybe even with a minus sign, so I get rid of this minus, and then this is equal to 1 over, so dk is dk tilde over psi1. So this is my point. This is the Jacobian I was talking about. And then you have integral from e to the minus, let's make it plus, who cares, k tilde Vm minus Vm over psi1 plus psi2 Vm, the small mass, psi2 over psi1. This is just the delta function. And then you get something that I guess you know. So this is 1 over psi1 delta function, because this is a delta function. And now of the variable that I care about, Vm minus Vm minus psi1 plus Vm psi2. Okay, and the psi1 comes all here. But I think you know this. So when I do this integration of Vm minus, I need to replace this Vm minus with this variable. Here I have a minus, if I put all this in a parenthesis. So again, I just replaced this. I get 1 over psi1 here, and then this Vm minus is equal to all this junk. So let me write it down. I just did one integral. It's very easy. So the equation is dw dt minus r dw. I'm not writing, it's of the massive particle, and then I have 1 over psi1 integral from minus infinity to infinity, the velocity of the small particle, w of Vm minus psi2 Vm tilde over psi1 f of Vm. So what I did here essentially is I used, was Vm minus, and then I just wrote Vm minus in terms of Vm after the collision given by this thing, and I gained this 1 over psi1 from the Jacobian. Now, how will we solve this equation? Or how will we make it slightly easier? You see, what do we have here? What is this type of integral? It's similar, but not exactly the same as a convolution. Because here I have Vm, here I have Vm minus, and I need to integrate, but I have here this psi1. So what do? You do the usual trick. You want to work in Fourier space. Because if you have a convolution-like equation, then it's much better to work in Fourier space. And then at the end of the day, I can invert it. So let us define w, k, and t as the integral from minus infinity to infinity, e to the I, k, capital Vm, w, Vm, t, dVm. It's just the Fourier transform. So when I perform the Fourier transform, this will be the Fourier transform. It depends on time. This will be the Fourier transform. I need to understand what is the Fourier transform of this object. Mm-hmm. So I need to know what is 1 over psi 1, integral from minus infinity to infinity, EI k Vm capital. Then I need to have here integral from minus infinity to infinity, dVm W Vm minus psi 2 Vm tilde divided by psi 1 Fvm tilde. Okay, so what we want to do is the following. Let us define x as Vm divided by psi 1. In some sense, we're going backward now. So if x is Vm, so let us do it carefully. So then I have dVm is psi 1 times x dx. So then I have this is equal 1 over psi 1. EI k Vm is psi 1 times x, integral from minus infinity to infinity, integral from minus infinity to infinity dVm tilde W x minus psi 2 over psi 1 Vm tilde F Vm tilde, and dVm is psi 1 dx. Now we'll do another change of variables. X minus psi 2 over psi 1. I could do it in one step, but this is y. So this is equal, first of all, this cancels and this cancels. Okay, so here I have the following. Integral from minus infinity to infinity, EI k. Now I need to write here y plus psi 2 over psi 1, Vm tilde. This is this x. Let us write another integral here, minus infinity to infinity, this integral. Wy, this is y, Fvm, and here I have dVm and dx, dy, dy. Because all this junk is y. And now you see what happens. Because you see I have here now, I managed to have two integrals, and both of them are Fourier transform of two independent functions, which is exactly very similar to Fourier convolution. So with respect to y, I just have the Fourier transform of w. So this is equal the w, the Fourier transform of k, which in principle depends on t. And here I have f, the Fourier transform of psi 2 divided by psi 1 k. No, but I made a mistake here, because here I have psi 1. Psi 1. And here I have no psi 1. Here I have this psi 1, I replace it x, y plus something, so here I have psi 1. So this is EI k psi 1 y psi. So again, what is this f? F of k is the Fourier transform of f of v. The velocity distribution of the gas particles. You take its Fourier transform from Vm to k. And then you get this. Here you see the effect of collision. You have psi 2 times k. And here you have psi 1 times k. And the Jacobian is killed. So, what do I get at the end of the day? D over dt, the Fourier transform of the velocity of the tracer particle is minus r, the Fourier transform of the velocity of the tracer particle, plus, because we have a minus term and a plus term, w k times psi 1 t. This is again a Fourier transform, and this tilde is again a Fourier transform, but now this function is independent of time, k. It might look to you an easier equation than the beginning, but notice this is not a differential equation. Because here I relate, it's non-local. This is a non-local equation because here I have k, here I have k, fine, I'm happy. But here I don't have k. This is psi 1 times k. And here I have psi 2 times k. So I'm relating different k's on, if you want, different values of this argument with this argument. So it's not something so easy to solve or a priori. I'll give you the solution, and we'll explain the solution. And in the write-up that I have on my web page, you can also find the mathematical way to get the equation, but to get the solution. But I'll just explain the solution, and you'll understand the solution, I hope, without understanding all. How would you guess the solution if you knew nothing about the process? You'll be in a problem here. But there is a simple way to derive this if you understand the physics. So let me write down the solution. Which you can check. I mean, once I give you the solution, you can just put it in here and check. There's a different issue how you get the solution, but the solution is given by, in Fourier space. Later on, I have to invert it. OK, that's a small problem. Is given by this. Sum over n equals 0 to infinity, rt to the power n, e to the minus rt, n factorial, times eik v of the massive particle psi 1 to the power m. So this is the initial velocity, psi 1 to the power n, pi I equal 1 till n, the Fourier transform of the velocity of the gas particle times k psi 1 n minus I psi 2. This is the solution for any velocity distribution of the gas particles. What does this describe more or less? What is n? What is the meaning of n? Can anyone understand what is the meaning of n? It was already in there. What is n? What does it physically mean? What is n? The number of collisions in the interval 0 of t. So you have realizations of this process where the number of collisions is 0, number of collisions is 1, 2, 3. Of course, if t is large, the probability that you will have 1 or 0 collision is very small, but there is some probability. And you see this from here. This is the Poisson distribution. This is the probability. So what is the Poisson distribution? You should know it, or maybe you know it. P. She cannot go to these talented voices. Pn of t is RT n e to the minus RT n factorial. That is the probability of n collisions in the interval 0 of t. And it's a famous distribution, the Poisson distribution. Again, I said it before. It describes, for example, decay, radioactive decay, and many other problems in nature. So this says, okay, you have certain probability of n collisions. And then what does this guy say? This is maybe slightly more difficult to immediately see, but from this you understand what this is. This is essentially, this guy is the probability of finding V given that you had n collisions. So if I have exactly n collisions, I know my velocity eventually in distribution. I know it. Because if I had, let's say, one collision, okay, I collided once, and then I get something else. So, of course, all this is written here in Fourier space. So this is the Fourier transform of this probability of having a probability. This is the PDF of V given n collisions. Let us see this. How will we see this? Let us consider what happens, for example, n equals 0. So, for example, n equals 0. What is your velocity? This means, let's say, if your measurement time is not long and you had no collisions. So what is your Vt? It's simply V0, the initial velocity. And you see here, when n is equal to 0, I need to interpret I from 1 to 0. This is just 1. So all this junk is 1. So I get EIKV0 in Fourier space. But what is this in real space? This is simply delta of V minus V0. So if there's no collision, you started with velocity V0, and at time t, your velocity is still V0, but this is because there's no forces, and we assume that between collisions, nothing happens. If n is equal 1, what is V of t? So you had only one collision. Notice that you don't care when was the collision during 0 and t. You don't care if it was at the beginning, at the end, because I'm looking at the velocity. So I had a collision, and then the velocity was V0, and then suddenly it changed with the collision to some other value. So what is V of t in this case? According to the rules, it's Xi1 V0 plus Xi2 Vm from the first collision. I have only one. If you want, you can add here an index, collision 1. So what is the Laplace the Fourier transform of this object is EIK V0 times Xi1 plus Xi2 Vm1. And what is the meaning of the distribution function? This is the Fourier transform. What is the random variable here? This is this V1 of the velocity of the. So I need to integrate this. You see how much easier it is to work in Fourier, of course, as usual. And you immediately see that this is equal. Okay, this thing you are not integrating over, but this is equal EI K Xi1 V0, and you remained with the Fourier transform K times Xi2. And this is exactly what is written here if n is equal 1. Psi 1 to the power 1 times v0. And here I have a sum from 1 to 1. So I have a multiplication only of one term because I had only one collision. And you see if this guy are equal, psi 1 goes away, and I have a k times psi 2. And what will be the case? Let's do one more step. Let's say n is equal to. If n is equal to, then what is the velocity at time t, again, of the tracer particle? Now I had a collision 1. And after collision 1, I had another collision. So it is psi 1 times psi 1 v0 plus psi 2 vm1. This was the velocity before the second collision. Then I have to add plus psi 2 vm2. And this guy are independent random variables drawn from the same velocity distribution, which was given by this function f of v, which again is in some cases Maxwellian. So EIKV for n equal 2, this is conditional probability when you have exactly any two collisions, which is this guy with n equal 2, that is equal to integral dvm1, integral dvm2, exponential ik psi 1 v0. Here I have another psi 1. Plus psi 2 vm1 plus psi 2 vm2, and I have here dvm1, the first collision, the gas particle, second collision of the gas particle. Then, first of all, I have a relaxation term. A relaxation term is how does the initial velocity decay? It's very simple. It's given by exponential ik psi 1 to the power 2 v0. Why to the power 2? Because I had two collisions. So what happens after each collision? The initial velocity is multiplied by psi 1, and then again twice. And again, this is the same as this one here. And then I have here, all this is in the exponential. And then I have here vm2 and vm1. So here I have times f. This guy is psi 1 times psi 2 k in Fourier space. And this guy f is psi 2 times k. Why? You see what is happening here. You had two collisions, collision number 1 and collision number 2. Collision number 2 is more important in the sense that it's not multiplied here by psi 1. So the collisions are, the older collisions, the ones that were at the beginning, the first collisions, are kind of multiplied by psi 1, which means they become less important. It's like the initial velocity is multiplied by this guy, so it's a decay. This is the relaxation. And then a new one appears with this psi 2. And again, this is, of course, if I put here n equal 2, so you see that I have here one term with k times psi 2 and one term with k psi 1 psi 2. So it's very easy to understand this from a physical point of view. But we can also check that this is the solution. Let's do that. It's very easy. The difficult part is if you don't know the solution, to find the solution. That is what you can see in the notebooks. But to see that this is the solution, so what you need to do is you need to take the derivative with time of this object. Why? Because you see here, I'll take the time derivative, then I have to get one term and a second term. And you immediately see why this will happen, because you have 2 times t. So when I take the derivative, I get one term from here and one term from here. In fact, when I take the derivative of this exponential, I get minus r. So it's very easy to understand that this is equal minus rw. This is when I take the derivative of this guy. And now when I take the derivative here, first of all, I have to notice that taking the derivative here, I need to start with n equal 1. Why n equal 1? Because if n is equal 0, then I don't have a multiplication. I have only one term. So I start here with 1. And then the derivative is r. And then I have rt n minus 1 times n. This is t to the n. I take the derivative divided by n factorial e to the minus rt. Then I have all this awful junk. EIKV, the initial velocity psi1 to the power m, I equal 1 till n, f k psi n minus 1 psi 2. And all this term has to be equal to this term. That is pretty easy to show. So first of all, n divided by n factorial gives you n minus 1. Sorry for this. This is n minus 1 factorial. Then what you do, you change, let's call n minus 1, let's call this is equal m. So this is minus r w sum plus r sum over m. M is bad because m is the mass, but never mind. Most likely you already don't listen anyway, so. Yeah. A proof of life from outer space, good. So, okay, so we have, this will be from 0 like before. And here we have e to the minus rt. And here you see I have EIK, v initial velocity psi1. Now, here I want to write it as m plus 1, because n goes to m plus 1. And then I have here pi, I equal 1 till m plus 1, f k psi 1 m plus 1 minus 1 psi 2. No, this is an I. This is an I. This is psi 1. Now you more or less can see what is happening here. If I define, I take here k psi 1 and call it k tilde. Then also here I have, from this plus 1, I have k psi 1. I'll also have a tilde. K. But otherwise, it's exactly the same as this definition. You see m minus 1. Here I have k times psi 1, but this m will remain the same. So this means that I get exactly what I have here. So this is equal, if you think about it a little bit, exactly what is written here. There's a mistake. You see, this was worthwhile. Here there's an R, because otherwise the units will be wrong. Made a mess here. Yeah, so another thing to notice is this +1, which means that I also need to multiply. I have one more term. When I switch this to, I write it as a multiplication till m, and then I have one more term. But when I is equal m plus 1, I get here f times k times xi2. Okay, so this, okay, I did it a little bit quickly, but just go over this algebra. It's not difficult just to take the derivative and see that this is a solution. And just to prove it, this was just my point. But more importantly is to understand each one of these terms here and where they come from. And they come from simple physics. But now we have an infinite sum. So this infinite sum, okay, if this f is a Gaussian, then you can invert it. But in general, you cannot invert it. So now we want to approximate this. We want to approximate the solution. Actually, we want to approximate this equation in a limit where the collisions are very frequent. The time between collisions is very short. And when this xi1 and xi2, they depend on epsilon, remember? When the mass ratio is small. So again, I'm repeating what I said before. The goal here is to say, okay, we had an integral differential equation. However, and then you have jumps in velocity, each collision. For example, if the masses are the same, what happens if the masses are the same? You have some velocity, and then it collides with the gas particle. What happens to the mass of the velocity of the big particle? It becomes the velocity of the gas particle. They simply exchange velocity. So boom, one collision, and you are in equilibrium. Which means the following: if the masses are the same, the particles collide, and then the big particle has the velocity of the distribution of the velocity of the small particle. So we are looking at a process where the mass ratio is the opposite limit. That would be called strong collisions. We're looking at the weak collisions. So you have these very small changes, but very frequent changes. The ratio of the masses is small. And then from this equation, which is a non-local equation, or from the integral differential equation, we get a Fokker-Planck equation. And this is our goal. And how do we get it? So you see this xi1 and you see this xi2. These depend on these epsilons, if you remember, on the mass ratio. So all I need to do is I need to expand this solution in k space in epsilon. And that's what I'm going to do now. I'm going to expand it, and then you'll get some magic. Boom, you will see Fokker-Planck equation. So let's do that. So from the Maxwell equation to the Fokker-Planck equation. So first thing we need to remember, what was xi1 and xi2. Xi1 was 1 minus epsilon 1 plus epsilon, and Xi2 was 2 epsilon 1 plus epsilon. Again, this was from the basic elastic collisions conservation of momentum and energy. So again, only this term, the second term, is non-trivial. I mean, the rest is trivial. So what we want to look at is that on RW in Fourier space, kt times f psi2 k. Again, the Fourier transform of the velocity distribution of the gas particle. That is equal to R W. I'm going to use that this guy is 1 minus 2 epsilon. This is an approximation when epsilon is small. So this is 1 minus 2 epsilon k at time t. F and Xi2 is going to be 2 epsilon. 2 epsilon k. So here epsilon much smaller than 1. So what do I need to do here? I need to Taylor expand both terms and then pray that epsilon will go away and etc. I mean, in the long time limit, I mean. So let us look at this. You have W 1 minus 2 epsilon k t. That is equal, in the leading order, you just take epsilon to 0. That is equal W k t. Then you expand it. And what is a small parameter? You see it's 2e times k. So this is equal minus 2e times k d over dk w k and t. And what is, okay, now let's think first of f of k. What is f of k? I didn't multiply yet by epsilon, but you see from this epsilon, what do I need to do? I need to look at the small k, because epsilon is small. What is this? This is 1 minus k squared, the velocity squared of the gas particle divided by 2, plus more terms. This is simply because we assume the velocity, the average velocity of the gas particle is 0. This is the usual normalization, and this is the characteristic function of the velocity distribution. So this is its a small k expansion. And there is some velocity spread, I mean something. If now we assume that this is thermal equilibrium, then we know exactly how to relate this velocity distribution to temperature. That's if you want, this is our definition of temperature. What is temperature? The variance of the velocity of the gas particle. That's how we define temperature. Divided by mass, of course. So f of k is 1 normalization minus k squared over 2. This comes from the Taylor expansion of the exponential. And here we have k Boltzmann t divided by the small mass, because we are dealing now only with the gas particle. So this is the small mass. Again, this is equipartition. There are more terms. And that's why f of 2 epsilon k, when epsilon is small, is equal 1 minus 2e k all this squared over 2 k Boltzmann t over m. Then we can what we care about is the multiplication of these two terms. So let's call this I because it was an integral. Now we just call this I, and now we just, what we do, we plug in this junk times this junk, and let's see what happens. So we have W k of t minus 2e k d over dk w k and t. There's more terms, and if you were rigorous mathematicians or even physicists that are, this is really your business, you would look at these higher order terms and you would try to prove that they are small. But this is not in class. This will take some time. So we don't do this. We assume that we cut off the expansion to leading order in some sense. And here, what do I have? Now I need to multiply this by this f, this one f. So the leading term is 1. This is, again, this normalization, minus 2e k squared over 2 k Boltzmann t divided by m. And there are more terms, but we neglect them. So first of all, you see here I have w times 1. This will cancel this minus term here. So let us now use this and see what happens. So I have the derivative, this is this term, the derivative with respect to time. Remember, our goal is to find the Fokker-Planck equation. The Fokker-Planck equation has the time derivative of the velocity distribution. This is part of our goal, of course. So we like this term. Minus r w plus, now I need to take this r times I, so I have r. And now let us write it. You have a w term. This is simply this times this. And then we have the following. Okay, so here it looks a little bit complicated, right? Because look what happens here. We have here epsilon. That's a small term. Here we have epsilon squared. But look, you have this small mass here. So if you think about what is epsilon, is small mass squared over big mass, and here you have small mass. So this term epsilon squared is actually the same order as this epsilon, as I'm going to show you right now. But of course, when you have epsilon times epsilon squared, then this I'm going to neglect, because I also neglected it here. So then I have minus 2 epsilon k d over dk w. This is just this guy times this guy. And then I have this guy times this w. So here I have I want to write it with a minus sign. So I have k squared. Then I have I have here a mistake. Okay, k squared, I have here a 2, because this is 4 divided by 2. Epsilon squared, this is this epsilon, and then I have here k Boltzmann t divided by m, and then I have here the w. Yeah, I have a mistake in my notes. This goes upstairs, you know. No, this is okay. Sorry. Okay, so now we are more or less ready. you see we have here r times 2 epsilon. So we are going to define gamma, which is the relaxation, 1 over the relaxation time, which is like the Stokes law if you want. This is the limit of epsilon to 0, r to infinity if you want, of 2 epsilon times r. So what am I doing here? I'm taking the collisions to be weak. That means epsilon is going to be small. And I'm taking the rate of collisions to be high. That means the time between collisions to be very short. So this is weak and strong collisions. Weak and frequent collisions. You don't really need this limit. I mean, what I mean here, epsilon is small, but I look at time scales, that t times r is already big. If I look at time scales which are very, very short, before the first collision, well, let's say the time between collision is 10 to the minus 15 seconds in the real system. If I go and look at what happens to our particle in times which are 10 to the minus 100 seconds, well, nothing, because the first collision happens after 10 to the minus 15 seconds, right? Nothing happens to in this time scale. But I don't care about this time scale. So I look after several collisions. So mathematicians, the way they do it is like this. They take the rate to infinity and epsilon to 0. But it's fine even if you want epsilon to be finite and r to be finite. Then what we really mean is r times t is of order 1 or after some short time, that you have several collisions. So this is the meaning of weak and frequent collisions. And then what you see here is, first of all, there is a cancellation of this term and this term cancel. This and this term cancel. And you have only 2 terms, this term and this term. We know that there are 2 terms because we know that in the Fokker-Planck equation there are 2 terms, one describing relaxation and the other one describing diffusion. So what do we get? We have d dw over dt is equal to minus gamma. You see r times 2e k d over dk w. And here I have r times 2 times epsilon. Okay, so here I'm going to use epsilon divided by m. What is epsilon divided by m? Is 1 over the capital M. And then here I have minus k squared, k Boltzmann t divided by m gamma w. And this is, of course, the Fokker-Planck equation. For the velocity of a Brownian particle, I taught you this two lessons ago, something like that. Because now what do we need to do? What is the last and simple step? To invert it. Well, what is k squared when you go back? Remember, k is the Fourier transform of velocity. So what is k squared? Is the second derivative of velocity. So I have here d over dt, w of, without a bar now. Now I'm in velocity, vmt. That's simply the inverse Fourier transform of this thing, equal gamma. I'm going to use this term for first, k Boltzmann t over m. Second derivative of velocity. So remember, because of the ik, you get the minus, and this gives you the second derivative of the velocity. And what is k d dk? So k is the derivative of velocity. And what is ddk? It's the velocity. Because everything, when you go from Fourier to velocity, k goes to the derivative with respect to v, and d of dk goes to the velocity. And then what we get here is plus d over dvm, vm, w vm t. And this is what we looked for all the time. This is the Fokker-Planck equation. You have here the usual kind of diffusion in velocity space. So if I didn't have this, the particle this would be like a diffusion equation. So this describes the fluctuations of the velocity, but in addition you have this relaxation that describes you the average relaxation. For example, if I multiply here by v and integrate, what do I get? I get the average velocity. This time gives me nada because it's the first moment when I do integration by part, and then when I do here the integration by parts, I get v dot minus gamma v average, which is the Stokes law. But now we identified what is gamma. It's 2 epsilon times r. It doesn't mean that this is valid in liquid. It's valid in this approximation, maybe in gas. In liquid, it's much more complicated. And it's also not a full explanation because we didn't say what r is. From this, we get the equilibrium. What is the equilibrium of this? This is very simple. And the long time limit, this goes to 0. And then in the long time limit, you get the Maxwell distribution. So limit t to infinity. And we know the solution of this equation. This is actually the solution. I solved it 2 weeks ago, but also last week. But last week there was an x here. I don't know if you see this, but last week, or maybe you don't even remember last week, but last week I had a particle which is overdamped in harmonic potential. And the particle in the overdamped harmonic potential had a linear force. So this was x. This was x instead of v. But it's exactly the same equation. So for the equation for the velocity and the equation for the overdamped Brownian particle in a potential harmonic potential are the same. So this process is very famous in stochastic systems. It's called the Ornstein-Uhlenberg process because it describes two problems, both the velocity of a Brownian particle, not overdamped, and an overdamped Brownian particle in an harmonic potential. So you know the solutions. You can look at them on the Wikipedia or wherever, Ornstein-Uhlenberg. It's also described by Langevin equations. So many people have their name on this. But importantly, W, V, and T is some normalization exponential minus mv squared over 2k Boltzmann T. So, of course, this is what it should be because we know this, but what I wanted to show you here is that you can derive this distribution, and if you followed what I said, it comes from several reasons. One of the reasons is, of course, that you assume that the gas particles have some velocity squared average, which is finite. So you have something finite, let's say Maxwellian themselves. But what is the other main ingredient to get here m, which is independent of the small m? What was it? It was the conservation of energy and momentum. The fact that I have here exactly 2 came from these definitions. If I had here something else, I would get, a different number. So this comes from, first of all, we have many collisions. Why many collisions? Because I take t to infinity, and r is either finite or infinite. Either finite or infinite. That means time between collisions is very quick. So we have many collisions, and then we get equilibrium, and we have plus energy momentum conservation. If I would not put energy momentum conservation into this game, for example, V after collision is some A times V before collision plus B times the gas particle velocity, all these numbers, all these cancellations that you add small m downstairs and then multiplied by epsilon, you see here, if these were just small numbers, they're not just small numbers, because I needed the fact that this epsilon is mass divided by big mass. And then I got this mass. And then I got here this mass and no small mass. If you do it in general, like a mathematician, you will get here some two numbers defining the collisions, and you will not see that you get an equilibrium which is independent of the gas particle. So energy momentum conservation was super important in the derivation of this well-known law. Now, we solve this problem in this limit of weak collisions, but I want to focus a little bit more just on the long time limit. Of course, this describes all the dynamics. How does this packet evolve in time? It starts with a delta function, then it spreads, eventually it'll reach in thermal equilibrium. But I want to emphasize one more point before we leave, and that is only related to the equilibrium. So instead of looking on time, let us say the number of collisions n is the number of collisions. Let's say n is much bigger than 1. I don't care how this big number happened. Any process could lead me to that. Maybe the collisions come after 1 unit of time, like on time 1, time 2, time 3. They're not necessarily Poisson distribution. I don't care, but n is big. Then I have a velocity distribution. So I have v0, then it goes to v0 times psi1 plus psi2 vm1. This goes to call all this capital V1. This goes to V1 plus psi2 Vm2, etc., etc. Each time you collide the particle, you don't care when, this will be the velocity of the tracer particle after 2 collisions. So you need to use this V1 in here, and then you get V3, V4, V5, etc., etc., etc. So if this is the case, what is the equilibrium distribution? This was already on the blackboard, so I'm just going to write it. The equilibrium velocity distribution in Fourier space after many collisions is given by the limit n to infinity f, you have a multiplication here, of I equal 1 till n, the Fourier transform f k psi1 n minus I psi2. And here I assume that the initial velocity is 0. Why did I assume it? Because I'm looking at the limit of large times, and I think it's already intuitive that you lose your initial condition, because you see what happens here. Psi1 times v0, then psi1 times v0 squared. This initial condition is damped. You forget about it because of the collisions. So in the limit, this is the equilibrium. If this is the equilibrium, you can have here any function if you want. If you want to play a mathematical game, you can put here any function f. And we would like to see when this guy is Gaussian. Without assuming that this guy is Gaussian. Of course, if this guy is Gaussian, then this guy is going to be Gaussian. But let's just pretend this f, the gas particle, comes from some general distribution. That's something. So how do you do this? You need to look slightly more carefully. We need to look at the Fourier transform of f of k. As I said before, this is 1. This is normalization. This is the expansion in small k. We have 1 times t over m. This is just my definition of what is the velocity squared of the gas particle. This is just a definition. It's not anything deep. This is like before. This is just, I'm only assuming the average velocity of the gas particle is 0. But what I want to show you now very briefly is you have here another term, k4. This expansion of f depends on the details. What is this velocity distribution? It's not universal. Our goal is to show that this guy is not important. So there will be some number, q4. This number is bad because if the eventual equilibrium distribution depends on q4, then the equilibrium is non-universal. And we know that the equilibrium is universal. It's simply Maxwell. So, and here I say, OK, here I have some scale, which is 2 over m to power 2. I want to divide this by 4 factorial. So we add something to the theory just to show that what are the conditions where this is not relevant for this guy in the limit n to infinity. So for that, we need to look at the log of WE equilibrium. Why do we want to look at the log? Because in that case, you see here I have a multiplication of functions. I'm going to take this multiplication of functions, and then there will be a sum, because I'm going to take the log. So this is going to be sum I equal 1 till infinity. Let's write it as to n. Okay, limit n to infinity, the sum I equal 1 till n, log of f k psi 1 n minus I psi 2. Now what do I need to do is I need to plug in this expression. In principle, I need the higher order terms also. I plug in this expression into here. I expand this. And then I want to show that when I sum, this Q4 is not important. If you do that, what you get is the following. You plug it in, 2 over m, epsilon k squared plus q4 minus 3 over 4 factorial t over m to power 2 2 epsilon to the power 3, 1 plus epsilon to power 2, k4 plus. I didn't do this calculation here. To do this part is relatively easy. Because what do I need to do? I have a log. Let's do the first term. I have log 1 minus t over 2m. Then I have psi1 to power 2 n minus I, psi2 to the power 2, k squared. I simply took this expression, and you have k squared. That's why I have psi1 to the power 2, psi2, etc. Now, I expand it. This is giving you minus t over 2m psi1 to power 2 n minus I, psi2 to the power 2, k squared. Now I need to sum this. I need to sum this. This is a geometric series. And the magic is if that you plug in here the values of psi1 and psi2, you get this epsilon. So I use specifically the specific values of psi1 and psi2. After summation, I get this epsilon. Then when I do the same with the first term, then I get one term which is q4 and one term because this guy you need to square it. So you get these complicated terms. The point is the following. That in the limit of epsilon to 0, so if epsilon is big, then there's no universality. This is obvious. If, let's say, epsilon is 1, the velocity distribution in equilibrium of the massive particle is the same as the small particle. But if epsilon to 0, then I get log of psi equilibrium. K is simply equal, see here I have mass over m, minus 2 over m k squared, and that's it. This is because you see here I get epsilon over m, but here I get m squared, and here I have epsilon to the 3. So this guy will cancel only the epsilon 2. You see here it cancels, gives you 1 over m. Here it cancels when you translate this to epsilon, but it remain an epsilon. So, and this is again, this term, which is not trivial, and I did not derive it here, which comes from this expansion, it comes only from the definition of what is psi1 and psi2. But what is this guy? This is, so what is the conclusion? The conclusion is that Maxwell distribution for massive particle is practically universal. Also, if Q4 is not equal 3, what is Q4 equal 3, do you know? It's the Gaussian. That means that this distribution is Gaussian, and then obviously this guy will be 0. Also, if Q4 not equal 3, we get Maxwellian. And this is exactly like the central limit theorem. No matter with what velocity distribution I start with, let's say uniform distribution, exponential distribution, my gas particles can be in any distribution. If they follow these collision rules and the mass ratio is small, eventually the big guy, the massive particle, which is, you can think about it as your thermometer, it will have a velocity distribution which is Gaussian, Maxwellian, independent, and that's the magic, independent of epsilon, or the mass, or the small mass, the rate, or Q4. It doesn't matter. All these parameters will not enter in equilibrium. You know this from statistical physics, but I hope only to convey that this comes from something very deep. Okay, so here we're going to finish. I'm going to leave you, if you have any questions. No.